Okay, thanks everyone for coming for the final talk. When complete the, I mean, I hope it's the final talk. But this is circular based IO. Maybe what will happen is that after part 3, part 1 will come again, and then part 2, and then no, maybe there is a circular dependence between the talks. But what is supposed to be hopefully the non-circular talks about circularity based IO, and the third lecture will be by Daniel Wichs. And Daniel, I know you have a hard deadline, so let's start.
All right, thanks, Baz. Thanks for being flexible on time, and thanks to all the organizers for organizing such a wonderful workshop. All right, so this is going to be the third part of this 3-part series on circularity-based I/O, and I'm going to tell you about how to construct another approach to get this type of I/O via something called oblivious LW sampling. And this is joint work with Hotech. Okay, so in this talk, we're going to follow the same framework that Giulio spoke about in the first talk. In particular, we're going to construct an intermediate object called split FHE. And Giulio already showed you that this notion of split FHE implies I/O. So the focus of this talk is just constructing this split FHE. And in this talk, I'm going to tell you about an alternate approach that's somewhat different from the approaches that Giulio and Roman spoke about for constructing split FHE. Just a little note of caution. So in our paper, we actually use a different term than split FHE, a slightly different notion that we call functional encodings. But for this talk, I'm going to ignore those differences and call it split FHE. So just a quick reminder what split FHE is. So split FHE allows us to encrypt some input X. It allows us to evaluate some functions over the encrypted input and derive a ciphertext C sub f that encrypts f of x. And lastly, there's a way to give a short opening, or I think Giulio called it a hint, which allows you to open this one particular ciphertext C sub f and recover the encrypted output f of x. And here we're going to think of f of x as a relatively long value, and we'll want the size of this opening that lets you open f of x to be smaller than the output size of this function. So there's some compression going on here. And the security says that even if I give you many openings for many different functions over the same encrypted input, these openings reveal nothing more beyond the outputs of all these various functions. And you can ask for either indistinguishability or simulation-based security. Here, we're going to focus on simulation-based security in the common reference string model. Okay, and so the way we're going to do this is actually by looking at a fully homomorphic encryption scheme. This is a small variant of the Gentry, Sahai, and Waters fully homomorphic encryption scheme. We call it the dual GSW scheme. And we'll see that this dual GSW scheme essentially almost gives you split FHE. It has all the right syntax. It has this nice small hint that you can give to open a long function output. The only downside is it's not secure as a split FHE scheme. If you give many openings, they might reveal more than just the function outputs. And to make it secure, we need one more tool that we call oblivious LW sampling. Very high level, oblivious LW sampling lets you create LWE samples without knowing the corresponding secrets. And so this is a tool that we abstract out, and we give a standalone formal definition of what oblivious LW sampling is. And we have a theorem that if you have this type of oblivious LW sampling and you combine it with the LW assumption, you essentially combine it with this dual GSW scheme, then you get a secure split FHE scheme, and that implies a secure IO. So essentially, this theorem says that if you want to construct IO, all you need to focus on is constructing oblivious LW sampling, at least as long as you believe in the LW assumption. And so one nice aspect of this abstraction is that this notion of oblivious LW sampling, maybe in contrast to other notions that we knew before that imply IO, like functional encryption or XIO or things like this notion really seems simpler. It does not involve any kind of general computation. It seems to be a simpler primitive. It doesn't talk about computing encrypted data in any way. It doesn't talk about computation at all. So, in some sense, it seems like we really reduced the problem to something hopefully simpler. And so the main part of the talk is then constructing this oblivious LW sampling. And we give a construction that uses LWE techniques, but it's a heuristic construction. We do not know how to prove security under the LW assumption. Instead, we'll prove security under a new but relatively simple to state indistinguishability type assumption, just that two distributions are indistinguishable from each other. And this assumption has some flavor of circular security that I will show you. So let me get started with the technical aspect of the talk. So let me start with the learning with errors assumption. I think most of you have seen it, so this is mostly just to set some terminology and notation. So here we have a random matrix A. Think of it as a tall and thin matrix. And we're going to take a random linear combination of the columns of A. So that's A times S for some vector S, plus some small error E. So here E comes from some small distribution, like a discrete Gaussian, where each entry of E is smaller than the modulus Q that we're doing this computation over. Okay, so this error has small entries. And the assumption is, I'm going to call AS plus E an LW sample with respect to the matrix A. So in this talk, we're going to think of the matrix A as fixed and look at sort of different LW samples with respect to the same matrix A. And the LW assumption says that this vector AS plus E is indistinguishable from just a random and independent vector of A. Okay, and so now I'm going to tell you about a fully homomorphic encryption scheme based on this LW assumption. That's a small variant of the Gentry-Sahai-Water scheme. I'm not going to tell you about the details of it. If you know GSW, it's relatively easy for you to see. Instead, I'm going to focus on like a few important aspects of this scheme that you need to know for this talk. So first, the scheme has a public key, and the public key is just this matrix A that you saw on the last slide. It's just a uniformly random matrix. And actually, in this talk, there's no secret key. We're never going to decrypt. There's not going to be any decryption. There's a way to encrypt some value X under the public key using some randomness R, and this outputs a ciphertext C. And then there's a way to evaluate a function F over the ciphertext to get a ciphertext that encrypts F of X. And I want to say a little bit more about the ciphertext. So here I'm going to think of a function with m-bit output where m is the same m as the height of the matrix A. And when you homomorphically evaluate the function f over encrypted data, you're going to get a ciphertext C sub f, which is a vector, and it has the following form. It's an LW sample, A times RF plus EF, plus the function output f of x times q over 2. Okay, so essentially the homomorphic evaluation produces an LW sample plus the function output. And the randomness of the LW sample is RF and EF somehow depend on everything, on X and R and everything that went into this computation. Okay, and furthermore, there's an efficient way. If you know the randomness of the encryption, you know the value that was encrypted, and you know the function you're evaluating, there's an efficient way to actually compute what this value RF is. And what that means is that I can actually give you this small opening, R sub f, that lets you break apart the ciphertext C sub f and recover f of x. So if I give you R sub f, you can subtract out A times RF from the ciphertext CF. You get f of x times q over 2 plus the error. And by looking at each entry and seeing if it's closer to 0 or q over 2, you can correct the error and recover f of x. So it looks like this scheme essentially already gives you something that's a lot like split FHE. So is it real? Is this a good split FHE scheme? Let's start with the good news. So the opening size here, the size of this RF or the hint or the opening that lets you break apart ciphertext is just n log q. And I can make n much, much smaller. So n is the width of this matrix, and I can make that much, much smaller than the height of the matrix, which is m. So here, the opening can be arbitrarily smaller than the output size of the function. I can get as large of a polynomial gap as I want. So that's good. What about security? So let's again start with the good news. So the ciphertext does hide the input X under the LWE assumption that you can prove. But that's not the security we want from split FHE. It's not just enough that the ciphertext hides X. We want to say that if I give you many openings, they don't reveal anything other than f of x. And unfortunately, that's bad. This does not hold here. If I give you openings R sub f to different values, they might reveal more about x than just the output f of x. And in fact, it's not just a potentially bad thing. We in fact know there's an attack. If I give you enough openings, you can at least distinguish one X from another. It's not clear you can like always recover X, let's say if it's random, but at least you can distinguish whether it's an encryption of one X or a different X.
Daniel, the reason for that is that RF and EF are not independent for different Fs?
The reason is that RF depends on R and X. So yeah, first of all, they're not independent. They're you know, they're all there's only one small amount of randomness in the whole system, and you're using it to create many openings. So certainly they're not independent, and they can depend on all of X.
Okay.
So so giving out these openings is in general not secure. So we're going to need to fix that. And
when you say we're revealing, so you're saying I should be thinking that the problem is that this is for different. I see this for many Fs.
That's right. That's one of the problems, that if you see it for many different Fs, then it's not secure. Even for one F, we don't have a proof of security. It's not. This might be problematic even for a single function.
Okay.
So actually, as a warm-up, to follow up on Chafi's question, let's see how to achieve security in the special case where I'm going to only give you one opening. This is just a warm-up that's not good enough for XIO or IO, but it will give us some intuition about what we need to do. And here's the idea. Let's just add a random LW sample to the ciphertext, just a random AS plus E, where E is going to be slightly bigger noise that's big enough to drown out this error E sub F. So it's going to come from a wider, let's say, Gaussian distribution. And I'm going to add this random LW sample to the ciphertext. Then when I do the homomorphic computation, I'm just going to add this LW sample B to the output ciphertext. And essentially, you can think of it as somehow re-randomizing the output ciphertext. And then to give you the opening, so just the ciphertext you get out when you do this, when you add in this value B, looks like this. It's just a combination of the original LW sample plus this red LW sample that was added in the encoding. And then to give the opening, I'm just going to open up this new ciphertext by giving you RF plus S. So that's this new secret S star. Okay, so that's the whole idea. Essentially, I'm just using a fresh LW sample in the ciphertext to re-randomize or somehow blind the opening that I'm giving you. And in fact, you can prove that this is secure. This is even simulation secure. The idea is that I can simulate the opening without knowing anything about the encrypted value or the randomness that went into the encryption. The way I'll do that is I'll pick these values S star and E star just uniformly at random. And I'm going to program this ciphertext B to have this form, AS star plus E star plus F of X minus the ciphertext CF. And you can see that everything, if I do this, everything works out. And in fact, this is the right distribution of B, except that the error is a little different. It has this E star plus E of F, but because E star drowns out E of F, E sub F, it's sufficiently bigger. This is the right distribution. So this gives me a simulation secure scheme for a single opening, but we need more than that. We need to give many, many openings. So how do we do that? How do we go beyond just one opening security? So maybe the first idea that you might have is that I can just add, instead of adding one LW sample to the ciphertext, let me add many of them. Let me add Q of them. And that way I'll get Q opening security for some, whatever Q I want, however many openings I want to give out. So that works, but unfortunately the ciphertext size would then grow with the number of openings I want to give out with this number Q. And we cannot afford that. That's not good enough for getting IO or XIO. Okay, so we need the size of the ciphertext to be independent, essentially independent of Q. Another idea you might have is, I said we can do this in the common reference string model. And so why don't we, so far we haven't utilized a common reference string. Why don't we add these LW samples, QLW samples to the common reference string? So the common reference string can be structured. So adding LW samples to it is not a big deal. But the problem is that in the construction, we need to know the secret S in the LW sample to give the opening. And so the scheme would need to have some trapdoor, some additional information about the CRS in order to create the openings. And that's not allowed. We are not allowed to use any kind of we can work in the CRS model, but we can't use any trapdoors about the CRS in the construction. It has to be completely independent of everything else we're doing.
Daniel, why can't you use many Bs but take like random linear combinations? In this way, you can compress a little bit, like in
yeah.
terms
So
of
random linear
that you want.
Very good question. So a linear combination, unfortunately, doesn't work because here I'm giving out the secrets S, and you would know the linear combination. So unfortunately, there's no security in this case. In fact, you can show this was like one of the first things we tried, and it's pretty easy to see that this is insecure.
Daniel, the requirement for avoiding use of S in openings, is this again a security requirement? Because functionality wise in the IO construction, the CRS would be part of IO, right? So it's okay to use it, but yeah.
Yeah, it would be. That's right. So in some sense, I need the CRS to be reusable, and so if I use some trapdoor for it in the scheme, I better make sure I can. It means it's not automatically reusable. Is it necessarily a problem for this simple solution? It would be. Maybe there might be some construction where you use some trapdoor to CRS that could be secure, but in general, it's more dangerous. You have to like prove that this is okay.
Yeah. Okay.
Whereas if you don't use any trapdoor, it's automatic, that's reusable, right? Okay, so these are two simple approaches that unfortunately fail. And the way we get around it is to define a new tool called oblivious LW sampling that essentially just lets you get around this problem. It lets you create many LW samples from some small amount of extra information. And so let me tell you on a high level, what we do is essentially combines the two ideas above, but getting the best of these two ideas. So I'm going to allow a long CRS, but the CRS has to be completely independent of the matrix A. So I can't put, let's say, LW samples in the CRS. I'm also going to allow some small value P that depends on A, but is small. It should be independent of Q, of the number of samples I want to generate. So I can't just put a lot of LW samples in P. I don't have the space. And we're going to think of putting this short value P as part of the ciphertext. If you have CRS and P, they will deterministically determine QLW samples, B sub I. And we're just going to use the ith sample to generate the ith opening, or to blind, to re-randomize the ith function that we want to open. Okay. I want to say that from CRS and P, you just get these LW samples B sub I. You don't get the secret S sub I. Here we need to also give S as part of the opening. So one way to do that is you can just generate A with a trapdoor and use the trapdoor to recover S from S sub I from B sub I and use that to generate the opening. That's a generic way to do it. The trapdoor, notice, is associated with this short value P, but it's independent of the CRS because the CRS does not depend on A. In our actual construction, there'll also be some randomness that goes into this, creating this value P. And if you know the randomness, you'll be able to figure out S sub I automatically, so you don't need to know the trapdoor for A. But in general, you can just choose A with a trapdoor and use that to recover S sub I.
Are the different SIs independent from one another?
Yes, I didn't tell you the security property yet. Let me start with a high-level security property, which is that all of these samples together should, in some sense, be as good as random. And I'm going to refine this on the next slide and show you the security property. But intuitively, yes, they should be like random LW samples. In fact, they should look like random LW samples, even if I give you the openings as sub I. That's the intuition. I'll make it clear on the next slide. I'll give you an actual secure definition. Okay. So this is the high-level idea. Let me actually give you the definition. So like I said before, we're going to consider a notion in the CRS model where the CRS can be very large. Depends on the number of samples Q I want to generate. And there's going to be this small value P that depends on the matrix A, but is small. There's a sample algorithm that's a deterministic algorithm. If you give me CRS and P, it outputs Q LW samples. So anybody can run this and figure out the samples. I don't need to specify anything else to specify these samples. And this is essentially what the honest scheme will use. For security, I'm going to require that there's a simulator, and the simulator takes some QLW samples BI hat as input. These are just random LW samples that gets as input. And the goal of the simulator is to program the CRS and this value P in order to cause the sampler to output the target values BI hat. So the simulator outputs P and CRS, programs them in some way. And the correctness says that when the simulator does that, then the sampler outputs the value that the simulator tried to hit. So essentially, the simulator can program CRS and P to make the sampler output these values that it gets as input. And notice the simulator doesn't know the SI hat. So it's not even sure that they're real LW samples, but has to cause the sampler to output them.
Is the CRS dependent on Q?
The size of the CRS can depend on Q, yeah.
And it's supposed to be computationally indistinguishable, I guess, the CRS output?
Yes, so this is the security property that you cannot distinguish between the real and the simulated version of the following tuple. So if you see the CRS, you see the matrix A, you see this public value P. So these are all the public values. But in addition, I'll actually open up all the LW samples that the sampler generates. You still cannot tell whether these were generated from the real distribution, where CRS is chosen randomly and P is computed this way, versus the simulated one, where the simulator gets these random LW tuples as targets and has to program these values.
Daniel, how short is P?
Just independent of Q. Any polynomial, but it shouldn't depend on Q. I think we can relax that a little, but we don't need to.
Daniel, isn't it an overkill what you're trying? Like eventually, if you go back to the previous slide, the adversary sees just EI plus the E, I don't know, E prime that were used for encryption. Here, it seems that even if the adversary sees both errors separately, then things will be, or at least, you know, this part separately, then it will be okay or something like
Very
this.
good point. Yes, you're absolutely right. I do think it's overkill. And we do have some, I'll show you later, we'll have some candidate construction that doesn't quite achieve this, but might be good enough. But we will have a candidate construction that achieves this. So it might be overkill, but the good news is at least it's good enough.
Thank you.
Good. So this is the notion. Actually, before actually, this notion is even a little too strong for what we achieve. We don't know how to achieve this exactly. We're going to consider relaxation of it. The relaxation might still be overkill, just to answer Benny's questions, but at least it's a relaxed overkill. And so in the relaxation, I'm not going to insist that when the simulator programs the CRS and P, he can get the sampler to output exactly the target values BI hat that he's trying to hit. There might be some mismatch between them, but I'm going to insist that the difference between them, that the value the sampler outputs includes the target value BI hat plus some LW sample for which the simulator knows the secret SI hat. And intuitively, this is good enough in the construction that we had because this BI hat will blind or will re-randomize the ciphertext. And this extra LW sample for which the simulator knows the secret won't hurt security in any way. So this relaxed version is good enough. And this will be what we'll aim to achieve. Okay, any questions? Good. So that's the notion. And so let's talk about this notion of oblivious LW sampling. So we proved the theorem that if you have this notion, it's essentially good enough in the construction. I think maybe that's already looks pretty simple, or it's fairly clear to you when you saw the construction. So this is good enough in the construction I showed you before to get split FAG, and then that's good enough to go all the way to IO. So essentially up to the LW assumption, oblivious LW sampling implies IO. Now, you might think that maybe oblivious LW sampling is in some sense overkill for IO. Is it something you can even hope to achieve? So the good news is that there's actually also a converse. So assuming IO, we can actually obliviously sample not just from the LWE distribution, but from all distributions in a very strong sense, even much stronger than this kind of oblivious LWE definition that I showed you. So that shows that actually, IO implies that oblivious LW has to be possible. Oblivious LW sampling has to be possible. And it was actually a previous open question if you maybe oblivious sampling, not just LWE, but in general, could be something easier. Maybe you can do it without IO. And so in some sense, our work says not really, because it implies IO. So if you do it, you'll already be most of the way there, at least up to the LWE assumption. And sort of similar to what Yael talked about yesterday, you can interpret this as a pessimist or an optimist. So if you're a pessimist, you'll say, oh, this really means that oblivious LW sampling is hard because it implies IO, and IO we know to be hard. But in this talk, I want you to be an optimist and to say, oh, actually, it means IO is easy because all we need to do now is just to do oblivious LW sampling.
By the way, Daniel, I don't know if you had a chance since yesterday. Did you figure out what sort of oblivious sampling would imply a quantum algorithm and what sort of oblivious sampling doesn't?
No, I haven't. I wrote Chris an email. I'm really curious about it. Yeah, sounds really fascinating, but I haven't been able to look. So
yes, yes. I think somehow with the quantum thing, it's somehow if you can generate this quantum state that looks like AS plus E, but somehow generate it while forgetting the S and the forgetting the S and the E while doing it, then somehow this is useful for quantum algorithms. But probably in particular, it needs to be statistically, and you might need to also to generate each one of those samples independently. So it might.
Yeah, this is definitely not statistical here. You need a computation assumption, so then that might be a big difference. Yeah, it sounds fascinating though. I'd like, for future work, I guess. Okay, so let's see where we are here. So we have this theorem that oblivious LW sampling and the dual GSW scheme give you split FHE, and so now all we need to do to get, which then gives you IO. So all we need to do to get to IO is to instantiate oblivious LW sampling. And the way we do this actually is that we're going to use the dual GSW scheme itself as a tool for getting oblivious LW sampling. So we use dual GSW in two different ways. One, to combine it with oblivious LW sampling to get split FHE, but also to instantiate oblivious LW sampling. We're just going to do it by using this dual GSW scheme plus some pseudo-random function. So let me start with an initial idea for construction. This is not our full construction. In fact, we'll see it won't be secure, but it conveys a lot of the intuition of what goes on in the full construction. And then we'll adapt it. We'll fix it. So here's the idea. We're going to create a dual GSW encryption of a PRF key K. Just encrypt this PRF key via the dual GSW scheme. And then to obliviously compute LW samples, we're going to homomorphically evaluate this function G over the encrypted PRF key. So the function G uses the PRF key to sample, and for the ith sample, it's going to call PRF on the key K and some and the value, the index I. And it's going to use the output of PRF K and I to sample some LW secrets S and E. And then it's just going to output the LW sample AS plus E. So G of K just computes a pseudo-random LW sample. For every I, it looks like a fresh and random independent LW sample. But unfortunately, we can't compute just G of K in the clear because we don't have the key K in the clear. We have it encrypted. So we're going to homomorphically evaluate G of K over the encrypted PRF key K. And if you recall, that's going to give us a ciphertext that looks like this. So it looks like some LW sample ARG plus EG. This LW sample comes from the randomness or the homomorphic evaluation plus the function output G of K. Now, if you're paying very close attention, I cheated a little bit previously when we were doing homomorphic evaluations. We evaluate functions whose output is 0, 1 to the m. And we got the function output times q over 2. Here, I'm evaluating a function whose output is not 0, 1 to the m, but zq to the m. And I don't have that q over 2, but it turns out you can do this. Essentially the same ideas. So you get, when you homomorphically evaluate g of k, you get a ciphertext that looks like this. But g of k is itself an LWE sample. So so what you get then is just the sum of two LWE sample, a red LWE sample that comes from the PRF output, and a blue one that comes from the randomness of the homomorphic evaluation. And you can just take this output and call it the ith oblivious LW sample. So unfortunately, this does not satisfy our definition. There's no CRS, there's no simulator. I don't know how to program anything to cause these outputs to be the outputs I want. So this will not satisfy the definition, but it might already be good enough for the full split FHE construction. And we discuss in the paper and give some assumption or write down an assumption under which this is secure. It doesn't look too bad, but that's not our ultimate goal. We actually do want to instantiate the definition I showed you before. So to do that, we'll need to do something just a little bit more complicated, but essentially using the same idea. Any questions on this idea before I move on? Okay. So to get the construction of oblivious LW sampling, we're going to adapt this idea just a little bit. We're going to include a CRS where the CRS just consists of a bunch of random values in ZQ to the M. We're going to do something very similar as before. So the preprocessed version of this matrix A just consists of the matrix A and this GSW, dual GSW encryption of a PRFKK, plus some additional bit beta, which we're going to set to 0. And then to create these QLW samples, we're just going to homomorphically evaluate the following function. So it's a slight adaptation of the function you saw on the previous slide. So just like before, we're going to generate a pseudorandom LW sample, AS star plus E star, using the output of the PRF. But we're also going to add in beta. So beta is this encrypted bit, which is set to 0 in real life. Going to include beta times the ith component of the CRS. Okay, and the output of the LW samples are just going to be the outputs of homomorphically evaluating these functions G sub I. So the ith LW sample looks like this. It's just some LW sample that comes from the homomorphic evaluation plus the output of this function GI. But the output of the function GI is just this pseudorandom LW sample A star plus E star because beta is 0. Okay, so we get an LW sample that really looks the same as what you saw before. But now with this CRS and this extra bit beta, we actually do have a simulator. And here's the idea of the simulator. So the simulator gets these target values BI hat that he's trying to program. He's trying to cause the sampler to output them, and he can modify the CRS and P. And the simulator is just going to put these values, these target values BI hat in the CRS and change the flag bit beta to 1. So now when you homomorphically evaluate this function, beta is now 1. So you actually incorporate the ith component of the CRS into the ith sample. And so you get an LW sample of this form in the simulated distribution. Now, in both cases, whether the real distribution or the simulated distribution, the output is always an LW sample that somehow includes this pseudorandom LW, the red pseudorandom LW sample, A star plus E star. And the hope is that that should cause these to be indistinguishable. You can't tell whether you're in the real world where you don't have this B hat or in the simulator world where this bit is 1 and you do incorporate the B hat into the output. So that's really the construction, and the assumption is essentially just saying that this is secure, but it turns out that this assumption is not too bad to write down. It just translates to assuming that the following two distributions are indistinguishable. So you cannot distinguish the following two distributions whether beta is 0 or 1. So these are two distributions, one with beta 0, one with beta 1. So let me just read off this distribution. So first there's a random matrix A. Then there's a bunch of LW samples, BI hat. there's some encryption of a PRF key K and the bit beta that you're trying to distinguish whether it's 0 and 1. And if I stopped here, if I didn't go any further, then this would be indistinguishable under LWE. So this would all be good. But unfortunately, I have one more term in this distribution. And this is some openings of some of these LWE values, some SIs. I have to tell you what SIs are. They're essentially going to be the LW secrets contained in the homomorphic evaluation of the function you saw on the last slide. So if you homomorphically evaluate this function over the encrypted value, over the encrypted PRFKK and the bit beta, you get some LW sample, and I'm just going to set SI. So you get this LW sample. This is what the LW sample looks like. And I'm just going to set SI to be the opening of that LW sample. And the hope is that you can distinguish whether beta is 0 or 1. So that's the assumption. And the assumption has this. So I want to give you a little intuition about why we believe this is secure, or why we hope it's secure. So it has this circular security flavor. And if you look at it, so the SI I'm giving out includes some pseudo-random value SI star. And intuitively, this SI star, I'm hoping, hides any other information, hides whether, what this RG is, and hides whether beta is 0 or 1. So it should cause somehow SI to be pseudo-random. So that's the intuition, but you'll notice there's some circularity here. So somehow I want to use the PRF output SI star to say that it blinds, or it hides this value RGI, I shouldn't say commitment, encryption randomness, this value RGI, which depends on the encryption randomness. So I'm somehow relying on the PRF outputs to hide the encryption randomness. But on the other hand, I'm relying on the encryption randomness to hide or to protect the PRF key, which is encrypted in the ciphertext. So you see there's really this circularity in this assumption. Any questions on the assumption?
So Daniel, if you had like a vector of switches instead of a single switch, I know that things will blow up, but then could you prove it without the circular security? Like if we could switch separately, only for the ith query or something like this.
Not sure.
It's not clear that it solves the problem, right? I mean.
Yeah. So if you didn't encrypt the PRF key K here, you encrypted some other value, but then still gave out this value SI, where SI star was computed using the PRF output, then I could prove everything is secure. So really the question is, are you encrypting the PRF key itself or some other value? That's really what's the difference between we can prove secure and where we need a new assumption. But if I also encrypted some other value that's not the PRF key, then these LW samples that you would generate homomorphically, this wouldn't be the right opening for them. So you could sort of notice that I'm doing something different.
Right.
So how crazy this assumption for Q equals 1? I'm trying to see if you make it like really compact, right? So Q equals 1 will be like constant size assumption. Is it believable or almost as hard as the whole thing?
Good question. I mean, the good news is we know how to achieve Q equals 1 really easily with other ways. I'm not sure if you exactly try to do it with this technique, if you could even prove security for Q equals 1. Not sure.
One thing that's nice about this definition, if I understand, is that you have, maybe going to what you have tons of freedom because you only want circular security between the LWE and any PRF. So the PRF could be something completely crazy, could be one of those things that we typically model as a random oracle. So so unlike before where you had two very specific encryption schemes that you needed circular security between them, now you basically are free to choose any PRF as long as there exists one of them which has this circular security. That's good enough, right?
Yeah, absolutely. That's a very good point. And I guess it also goes to this point, whether you make the strongest assumption or the strongest one you find believable or the weakest one you need. So I guess the strongest one that find believable is this should work for every PRF, but we all, of course, only need it to work for one. So if you want to try to attack it, use the silliest PRF or the best one that you can hope to break. That would already be interesting. Okay, so so that's pretty much it for the technical part of the talk. I just wanted to spend a little time comparing the three works that you heard, the last three talks essentially. And the constructions are, they look different. I think sort of if you just look at them and look at the constructions, they appear to be, they have some similar ideas, but they look quite different. I think conceptually, there's actually a lot of similarity that is not apparent when you first look at them. So I'm going to give you essentially a translation table between the two constructions or how things match up. So in our case, we need this notion of oblivious LW sampling. I think this corresponds pretty closely to the other constructions where you needed to obliviously generate encryptions of small values. One nice aspect of our work is that we can actually abstract out this notion of oblivious LW sampling as a standalone tool, have a standalone definition that suffices. I think in the other works, it's not, there was no standalone definition of what oblivious encryption of small values mean, but intuitively, that was the main component you needed. The way we do oblivious LW sampling is we homomorphically generate a pseudorandom LW sample. So that's a very high level of what's going on. I'm skipping all the CRS and a lot of details, but at a high level, that's the main tool here. Whereas in the other works, you were essentially homomorphically decrypting a random ciphertext in the CRS. And homomorphic decryption, or just, well, decryption, is usually just inner product with rounding. And inner product with rounding is actually a good weak PRF. We could have actually used a weak PRF instead of a PRF. It wouldn't have made a difference. So maybe you can actually think that this homomorphic decryption of random ciphertext is not that different from homomorphically evaluating a pseudorandom function for a particular pseudorandom function. And lastly, in our work, we needed some circularity between the PRF key and the encryption randomness. Somehow the PRF key was protecting the encryption randomness and vice versa. Whereas in the other works, the circularity came from whether or not you have a key cycle in the context of this bigger SRL shielded randomness leakage security game. So slightly different forms of circularity. Also, if you look at the assumptions themselves, I think both works, the assumptions have circular security flavor, but the concrete phrasing of the assumption is somewhat different. So in our work, the focus was more on writing down a fairly simple assumption in terms of the core underlying algebra. So the assumption is non-interactive, just the two distributions are indistinguishable. It does not involve any general computation. Whereas in the other work, there was more of a focus of putting these assumptions into a broader framework where you can prove something without a key cycle, security without a key cycle, and then the assumption is just that the same type of security holds when you do include a key cycle. And having that framework is really nice for somehow getting a better conceptual handle of what these assumptions are about. I think in both cases, the intuition why we believe in circular security, but or why we think that these assumptions are plausible, but it's very hard to prove them, is that's actually a common concept in circular security. Circular security is often hard to prove. It's very hard to prove that even simple crypto systems satisfy simple notion of circular security. But at the same time, it often holds, and it's very hard to exploit circularity in attacks, because like to break one component, you need to break the other component. But to break the other component, you need to break the first one. So it's somehow hard to exploit the circularity in attacks often. I want to mention something that already I think Roman and Julie also mentioned. There is, though, I would say a significant conceptual difference between the type of circularity that we need in all these works and the basic circularity that's needed for fully homomorphic encryption. And the conceptual difference is in fully homomorphic encryption, you can hope that the adversary can't even tell whether there's a key cycle or not. He can't tell whether, you might need the key cycle for correctness, let's say for correctness of FHE, but the adversary can't tell if correctness holds or not. He can't, he might not be able to tell if the key cycle is there. And then because you can't tell the key cycle is there, it shouldn't hurt semantic security. Whereas in our works, it's very easy for the adversary to tell whether the key cycle, the circularity is there or not, because correctness requires the circularity to be there, and the adversary can tell whether correctness holds or not. So it's more like functional encryption, or this notion of split FHE. The adversary can actually see if he's getting the right openings if correctness holds. And therefore, in these cases, you need to assume that the circular security still holds, even though the adversary can easily tell that there is a key cycle or some circularity involved in the game. I think that makes these conceptually somewhat different. And let me just conclude by going over one of the big ideas that maybe encompasses all of the works that we heard about in the past 2 days. And the big idea here is that compression implies I/O. It's not actually even new to these works. It's already, this idea has been around from previous works. So somehow if you can, if you have some long function output f of x and you can reveal f of x in less amount of space, writing down fewer bits than just writing down f of x itself without revealing anything else about x, that's the key aspect of doing I/O. If you can do that, you can get I/O. And in the works you saw yesterday, the talks you saw yesterday, I think one of the big central components that already gives you this type of compression is quadratic FE. It already gives you compression for some functions, for quadratic functions. It's nice. You provably get compression. You get compression under nice assumptions, but you only get it for extremely simple functions, quadratic functions. And then many additional ideas, like you saw in the talk yesterday, are needed to bootstrap from these extremely simple quadratic functions all the way up to functional encryption or I/O or compression for general functions. On the other hand, today we saw that certain FHE schemes give you compression pretty easily for general functions. Let's say dual GSW gives you compression essentially for free. I can compute this big function and give you a short hint that that lets you recover it. But unfortunately, security is lacking. We know these schemes as they are insecure, and then additional ideas are needed to upgrade security. And I think it's really interesting to sort of think about compression under different assumptions. For example, if I just restrict myself to LWE, I don't know how to get any kind of non-trivial compression for any kind of function, quadratic, anything. So I think that's one of the big challenges if you want to build provably secure I/O from LWE. Try to just get any kind of non-trivial compression. That would be very impressive, and that's where the challenge lies. So let me end here. Thank you.
Very much.
So Daniel, can I ask you a
Yes.
question? So actually, have you thought about like a comparison between the assumptions between AJLMS and this? Like it looks kind of somewhat similar. Like in AJLMS, the first assumptions we had some nice LWE samples and then a polynomial leaking on the errors. Here also, like you could think of it as like some LWE samples and some leakage on the like the input you are encrypting, but you don't exactly get that. You also get some noisy terms. But what you can also do is like you can have a slightly higher degree. That's my understanding. Like flavor-wise, they are kind of similar.
Yeah, one nice thing about this type of works is we're not constrained on the computation. You can really do a lot. Evaluate arbitrary PRFs because we're not constrained to like quadratic things, and so that makes our life a lot easier, I think. But it's very hard to compare these assumptions. Like I don't even know how to compare. Forget going to AJLS, but even these three works you heard about now, which seem very similar, we don't really know how to compare the assumptions in them in any kind of a formal way.
Is there a way to unify these frameworks, the first three frameworks, like give a general family of assumptions where you can instantiate like all these?
It's a great question for future work. So none that I know of, but yeah, okay. Conceptually seems like there's a lot of similarity. It would be great to like build some framework of assumptions that let you unify them and maybe some Uber assumption that implies all of these. That would all be extremely interesting.
Daniel, is there a version of your assumption? I don't know if you already took away the slides, but is there a version which kind of you're saying this new assumption plus LWE is a way to maybe replace one of the samples by random or something and get like an assumption which implies like one assumption that implies LWE, just rather than two assumptions?
Yeah, I mean, sure, you can.
Yeah,
in fact, in the distribution I showed you, or the assumption I showed you, the there were two distributions, both of which included LW samples. And in fact, you know, the maybe more natural thing would be to put random values in one and LW in the other. So in some sense, we need LW.
Yeah.
We need LWE for we need LW for our oblivious LW sampler to be secure. But in general, it's actually not clear. In particular, IO implies oblivious sampling of everything. So you might be able to do oblivious LW sampling without the LW assumption. If you can build IO not from LWE, which might be plausible, you could obliviously sample all distributions with, you know, in particular LW distribution without LW assumption holding.
And also, I guess related to the question about which PRF to choose, is your intuition that if it takes the simplest possible, like, I don't know, some kind of PRF, I don't know whether it's LW-based PRF, but the simplest possible PRF, or should it be the messiest PRF ever? Which one makes the assumption more believable?
Probably for if you just care about security and don't care about proofs, take the messiest one. But if you want to have hope of proving anything, take the simplest one.
But so far, you basically assume, I mean, it seems like pretty much for every natural PRF, it's probably true.
We don't have any counterexamples, even unnatural PRFs, you know, do your worst. We don't know.
But you wouldn't be surprised by, like, if somebody gives like the same like counterexample of circular encryption, like some really, you know, if IO exists and there exists a PRF where this is not secure, it doesn't kill your result, but you wouldn't be surprised, for example, or I don't know.
I would be mildly surprised. I don't know what I'm surprised by anymore these days, but I would at least be mildly surprised. It does not seem easy to do that.
Okay.
Just because you don't get any outputs in the clear, everything is sort of, you know, yeah, so it seems hard to do that.
So Daniel, just to make sure that I understand, following Boaz's point about the existence of a good PRF. So let's put like Boaz, like the weakest version of your assumption, and let's try to negate it. What does it mean? So it means like it sounds like a, you know, a crazy world where whenever you, like, correct me if I'm wrong, right? I mean, if this assumption does not hold, then it means that whatever PRF you're going to use, once you have the circular dependency with LWE, things are broken. That's the kind of so
yeah, that's the world in which IO would not exist.
So that may be even, you know, useful if this is the world we are living in. Did you try to look at it as an assumption that you can exploit to get things like?
Great question. No, we did not.
Okay.
Good question.
Daniel, I had another question that's also related to this like arbitrary PRF thing. Do you think there's any hope of being able to like formalize an idealized model for the PRF, in which case like where you can prove your assumption, your construction is secure? Like I like the obvious objection is that you're actually homomorphically evaluating this PRF, right? But maybe there's still some hope, or maybe with a different construction.
Yeah, it's a good. I don't know how to formalize that, right? Because I do need the code of the PRF to evaluate it. So it's I don't know how to say it's an ideal object yet. I can evaluate it homomorphically, but
it just seems plausible. It seems plausible to me that maybe not with this construction, maybe with a different construction. That it would be nice to know, right? That like we don't have any results like LWE plus random oracle would give IO or something like that. That would be great.
Right. Yeah, that would be amazing. So yeah, I think the hard part for me is not, you know, would be how to even, well, if you just really were in an ideal model, that'd be great. But that seems very hard to make work with our high level approach, because we're really evaluating these functions under homomorphism, and I don't know of any, you know, how to formalize things otherwise, where you still have some ideal property, but you have the code at the same time.
So what we were trying to do, we're trying to do something similar in the first, the one from Eurocrypt work. And what we're trying to do there was to sort of try to sort of encapsulate a primitive and sort of instantiate this primitive in an idealized model, and then say, you know, if you can securely implement this primitive, then, you know, you can, if you have the code of this, then you homomorphically evaluate. This would give you sort of both in some sense use of idealized model in order to prove something, and then also, you know, once you have this part sort of compartmentalized, you're using the homomorphism on the code. So
that's similar to their oblivious LW sampling implies IO theorem, right?
Daniel?
I'm not
Oh, you're
sure.
saying
Yeah, because
that does oblivious element. Yeah, but even for the, I mean, it doesn't. We couldn't make it work, and I think Daniel also sort of the construction runs into the same obstacle that we don't know how to sort of push all of the random oracle into something that doesn't require homomorphism of the random oracle. We don't know
Sure,
how
it
to
makes sense. I'm just
Right.
saying the
So
result,
if you-
the
if
result
you
that you were
ideal-
able to prove is similar to their completeness for LW sampling, I think.
Yeah.
I think so. Like if you idealize the oblivious LW sampling itself as a primitive, like thought about that as an oracle that you just push a button and gives you an LW sample, then it would be easy to prove. But something just that doesn't have structure, like a random oracle, we don't know how to use that in any way.
Typically, people are happy when they can replace the random oracle with something which is a concrete property, right? I mean, like correlation robustness or things like this. So in a sense, you're in a better shape than just using a random oracle. You have a very concrete property, right?
But we need the code, so there's a difference, right? Like
we always need the code, right? I mean,
no, if you have like results in the random oracle model, don't need the code, right? They
but
just in a black box.
eventually you have the code, right? In the real world, you have the code, right? The random oracle is not in the sky. So I don't know. People like there are papers who replace a random oracle with something, the property that can be proved without a black box access to an oracle. So again, I think that moving to a random oracle, for me at least, this is the wrong direction, right? I mean, you're already in better shape.
Going back to your CRS thing, so you sort of need one mask for every evaluation of a function, right?
We need, yes, we need one LW sample for every evaluation, and the CRS is as big as the number of samples we output.
Is there any hope of doing things in the sense that if you could do Q+1 things with a CRS meant for size Q, does it amount to solving the problem essentially, or is it qualitatively weaker?
Well, I would say that actually we don't care about the size of the, we're good. It's good enough to have a long CRS. You still solve the problem, so we don't need to worry about the size of the CRS. You could ask if it's possible to do a small CRS. You won't get the simulation-based notion because the simulation-based notion requires programming. Where else are you going to program other than the CRS? But you might still get a good enough notion for the final construction.
Thanks.
So I actually need to run. Sorry, everyone. This is my time.
Thank you, Daniel.
I'm happy to answer any other questions if you have over email. Please don't hesitate to send, and I'll be sure to respond.
And let me maybe
Shabbat shalom.
Yes,
Shabbat shalom. Thank you.
And thank all the speakers of the sessions. We still have one more ramp session, which actually Yael will be running. Since I actually also have to go, I might be able to participate, but I'm not sure my internet connection will be good enough to run it. So Yael will be running the ramp session.
It's one. There's only one person signed, right? Signed up.
Only one person signed up. It's still not too late for if someone wants to, even with no slides, to just talk about something. Then I mean, Yael has complete autonomy.
Feels so powerful.
I want to thank Boaz for his organization and all the speakers. But Boaz, really good for you. Thank you so much.
I really learned a lot, and I think this was really nice. I'm very grateful for the speakers that they. I'm very grateful for the speakers that have coordinated together. So I think it wasn't like it wasn't just like a collection of these joint talks, but it was really something we learned from. And I think that these videos will be very useful also for the people that weren't there. Yes, so I think in 2 years, 1 year, when we have the workshop on obfuscation based only on LWE, maybe we'll say, okay, some of the benefits came from these discussions. So thanks everyone. I'll still try to join the ramp session if it happens.
So it starts in 6 minutes, right? 4:20 here.
Yes, 4:20 here, assuming the organizer, the one person that's signed up is not yet here, but let's hope he comes up in 6 minutes. And otherwise, you can just continue and still continue the kind of discussions that people have already been doing. So thanks, everyone.
Thank you.
Thank you, Boz. Thanks a lot.
Thanks, Boz.